Hello students. In this session we are going to discuss two-way analysis of variance without interaction. Two-way analysis of variance we use or apply when we would like to study the effect of two factors on the average outcome. Here I have considered an example from the agricultural research. In agriculture sector, most of the time the researchers would like to see the effect of fertilizer or variety of fertilizers that they are using to increase average yield. Similarly, variety of seed types on which different types of fertilizers are used to affect or influence average yield. So over here, what I have done, I have considered 4 different varieties of fertilizers introduced in the rows and 3 different types of seeds introduced in the column. And this is the data, let's assume, that represents the overall productivity when seed type 1 is interacted with fertilizer type 1. And since we have considered only one application, one observation in a cell, therefore we call it, this is the application of two-way ANOVA without interaction. Interaction effect we can capture when we apply or observe multiple readings in each cell, so that if variability occurs even when the same seed type interacted with same fertilizer type may cause different outputs. So we are controlling that factor and we are taking only one reading on the basis of fertilizer 1 and seed type 1, fertilizer 1 and seed type 2, and fertilizer 1 and seed type 3 respectively. So this is the data that I have considered. Now we will state first of all the null hypothesis and alternative hypothesis, and since we are dealing with two different factors, so both the hypotheses must be stated separately for the two factors. So H0 and H1, since we are considering the factors that we have taken in the rows, that is fertilizers, therefore we need to state the null hypothesis and alternative hypothesis for the effect of fertilizer on average yield separately as factor A. So we state this as there is no significant effect of fertilizer type on mean or average yield. There is a significant effect of fertilizer type on average yield. Similarly, we will write up the null and alternative hypotheses for the second factor accordingly. For factor B, that is the type of variety of seeds that are being used. So again, H0 is there is no significant effect of seed variety or seed type on average yield. H1, there is a significant effect of seed type on average yield. Now, as usual, we state the level of significance and just assume that you are asked both the hypotheses to be tested at the 0.05 significance level, and we usually take the same significance level for both. Test statistic would be based upon two F ratios, one for factor A that has the formula mean sum of curve treatment for factor A divided by mean squared error, and for factor B mean sum square of treatment for factor B divided by mean squared error. Now if we consider the total number of observations given in the table are 12, that would give us DF for SST as n minus 1, that is 4 times 3 is 12, take away 1 gives us 11. Degrees of freedom for the factor that we have introduced in rows, that is SSTR of A, would be R minus 1. Over here R represents the number of rows or the number of fertilizers that we are using, that is 4. Take away 1 gives us 3. Then DF of SSTR of A of B, factor B, that is the variety of seeds, we can indicate as C minus 1. C is for the number of columns. 3 varieties of seeds are represented in column, therefore 3 take away 1 would be the degrees of freedom. And DF for SSE we can determine as DF of SST minus DF of SSTR minus DF of SSTR A and B respectively. Therefore, that's 11, then minus 3 and minus 2, that gives us a 6. 6 as the degrees of freedom for sum of square of errors. Now we can write down or state the critical regions accordingly. For factor A, the degrees of freedom obtained from f.05. For this factor, the degrees of freedom are 3. For this factor, the degrees of freedom are 6. So, third column and sixth row would give us the value of 4.76. You can check from F table this value. This is for factor A. Now for factor B, which is the seed variety, no 0.05 with second column and sixth row gives us 5.14 as the critical value, and we state the rejection criterion or rules accordingly for both the factors as H0 would be rejected if FA calculated exceeds 4.76. That's the rejection criterion for the first factor, and that's the decision criterion for the second factor B. And now what I would do, we can enter all 12 numbers in the calculator to get the sum of squared and sum of x. Sum of x is already given as 1730 because that's represent the grand total. Whether we go for row wise totals or adding up column wise totals, we end up with 1730. So what I'm doing, I'm entering all 12 observations in the calculator so that we can come up with the values of sum of x squared and sum of x. So 138, the alternative way is to raise every value to square. 138 squared plus 132 squared plus 140 squared plus 146 squared plus 150 squared plus 144 squared plus 130 squared plus 140 squared plus 150 squared plus 150 squared again plus 148 squared and plus 162 squared gives us the sum of squared value as sum of x squared is equal to 250268. This we will be using to get the sum of squared of totals computed using this formula. Summation x squared, take away 1 upon n times summation x whole squared. That is 250268 minus 1 upon 12 times 1730, that's the sum of x or all values of x. So the final answer is 859.67. Now we go for SSTR of factor A. For SSTR of factor A, we need to focus on the row totals, that is 410, 440, 420, 460, that captures the total productivity on the basis of 4 fertilizers. And what we need to do, since we are capturing or computing variance, therefore we need to square each row total divided by the number of observations on the basis of which this total we have computed, and that's 3 different types of seeds. So 3 different values are added together, so we go for the average in this way. Then 440 squared divided by 3, then 460 squared divided by 3, and then 420, what I missed out, this should be 420, and then 460 squared divided by 3 minus 1 upon 12 times same 1730 squared. Now 410 squared plus 440 squared plus 420 squared and plus 460 squared, and what we can do, we take the sum and then divide in the end by 3 because the divisor or denominator factor is common, that's 3. So that's 249 249900 24 double 9 and double 0 minus 1 upon 12 times 1730 squared. And that's 491.17 is SSTR of A. Then SSTR of B should be computed as the column totals. So column total, first column total squared divided by this total we have obtained by adding these four values. So when we go for the average, we divide it by 4 then. Then 570 squared divided by 4. Then 596 squared divided by 4. Take away 1 upon 12 times 1730 squared. So 564 squared plus 570 squared plus 596 squared should be divided by 4, and it gives us 249,553. Take away 1 upon 12 times 1730 squared. So that's 144.67. Now we can compute SSE as the difference of SST, SSTR of A, and SSTR of B. So what we do, from SST, which is 859.67, take away 491.17, take away 144.67 is 223.83. Now we note down each sum of squares so that we can use these values and present it in ANOVA table formally. Now I am changing the page. Moving to the next page, we are going to present our results in ANOVA table. So ANOVA table we construct, in which the very first column is the source of variation, and there are three sources of variations. First of all, factor A, that is representing the effect of fertilizers. Then another source of variation is the seed type that we have labeled or denoted as B. Then we have error, and all makes the total collectively. So the sum of squared values are 859.67 is for total, For A, this is 491.17. For factor B, this is 144.67. And then for error, this is 223.83. Now we take degrees of freedom into consideration. Degrees of freedom are r minus 1 or 4 minus 1 or 3 for factor A, c minus 1 or 3 minus 1 equals 2 for factor B, n minus r minus c plus 1, that is for factor, that's 12, 4, 3 and plus 1, that's 6. And for total, this is n minus 1, which is 12 minus 1, 11. Now we divide each sum of square value by its associated degrees of freedom to get the mean sum of squared value worked out. So that's 491.17 divided by 3 gives us 163.72. Then for factor B, 144.67 should be divided by 2, gives us 72.335, and 223.83 divided by 6 gives us 37.305, that can be rounded up to 31. Now we compute F ratios for the two factors respectively. And F value for factor A can be computed as 163.72, which is this one, divided by this 37.31. And the answer is 163.72 divided by 37.31 gives us 4.388. This is what F ratio for factor A we have computed as. The F ratio for factor B can be computed as by dividing 72.335, which is mean sum square of factor B, should be divided by again error or mean sum squared error, which is 37.31. So 72.335 divided by 37.31 gives us 1.938, which makes it 1.94 rounded off to 2 decimal places. Now if we consider F decision criterion, that F for factor A we have identified as H0 would be rejected if FA calculated would exceed 4.76, and F for factor B calculated if it exceeds 5.14, then H0 would be rejected. If we compare these two values with the corresponding computed values, so both values of factor A and factor B does not lead us to go for the rejection. Therefore, H0 is not rejected, and we write down the decisions for both the factors as, since F calculated for both factor A and factor B does not fall in the rejection region, therefore H0 is not rejected. Also, for factor also we can draw or write up the conclusion as the test results for both same. The test results are not statistically significant, and data do not provide sufficient evidence to conclude that there is a significant effect of fertilizer and there is a significant effect of seed type on average yield. So there is in fact no significant effect. We can draw our conclusion as. So that's all for this session of two-way analysis of variance.